Okay, today's topic is machine language instruction set architecture. So to execute programs, the program written in a high-level programming language must be translated into a machine language program. And in general, there are two types of translator. The compiler translates a program written in a high-level language program into a machine language program. And as a part of the compiler, it usually includes an assembler, which translates symbolic machine language program, which is called assembly program, into machine language programs. And we'll do this assembly language programming as the first project in this class. The second class of translator is called interpreter. The function is it not only translate but it also execute the programs directly. Okay, and the example is a Java virtual machine. So there is a Java compiler that translates the program written in a program language called Java into a bytecode. Bytecode is a Java virtual machine instruction. It's like a virtual machine instruction, but it's not actual machine instruction. So to execute the Java bytecode directly, you have to translate into machine instructions in the host machine. So Java virtual machine translates Java program that are compiled so Java bytecode to a host or native machine instructions. Okay, so if you have Java bytecode, if the machine has the Java virtual machine, it can be ported to any machines because it can be translated into native machine code by this Java virtual machine. Okay, Java is like a virtual machine, but it requires another level of translation. Okay. And interpreter is also used in shells. Shell is a command line interpreter. Command line interpreter used in Linux or Unix. Or in a window, you can also type some Unix window commands and it translates and executes directly. Okay. So let's look at this compilation process briefly. And we'll study this process more in detail in the next topic, which is linking. Linking means we are trying to link multiple programs, multiple object files into a single executable files. So compilation process usually involves this kind of process. You are writing a program in C or C++, and using the preprocessor, you expand macros such as sharp define or sharp include. You copy the header files, you expand some define macros and translate into C programs, equivalent C programs. So it's called expanded source program, and then you need compilation. So as a function of compilation, you can directly generate assembly machine instruction, or you can generate symbolic machine instructions called assembly programs. So compiler involves this much step. Part of this process also includes this assembler, which translates program written in assembly instruction into machine instructions. So using the compiler option, you can generate object code directly, or you can generate symbolic machine code, assembly programs. And as a result of this compilation, it generates relocatable code. So this is an object file, binary machine instructions, but it's not executable. Because usually the object files, you sometimes call the function in a library. Then from the library, you have to extract the linker usually extract the object files in the library and connect together because some of the functions are defined in this library. Or some of the functions are also defined in another relocatable object files. Because when you develop some programs, you can develop programs by multiple people, right? Multiple persons. And each person independently codes its functions. And he can use another function that are defined by another person. And you need to link together to generate executable. So the final executable or target program should contain all the functions and variables that are required by your programs. So this kind of linkage is done by the linker. So linker, there are multiple relocatable object files. They link them together. And if some object files calls another function in a library, it also link the object files from the library and generate a single executable file. Library is a collection of object files, collection of relocatable object files. Okay, so there can be standard C library or math library. You can call some sine function or cosine function. You don't have to copy them all. You only extract the functions that are included in that object file. So you only copy those object files and link them together and generate executable file. And then you now have all the code and variables that are required to run your program. And then this becomes an executable file. So this is called executable file. This is relocatable object file. There is some difference. Okay, so the compiler is a program that translates a source program written usually in a high-level programming language into another equivalent target program written in usually machine language. Okay, and source program is usually written in high-level programming language such as C or Java, and the target program is written in machine language such as x86 or Spark or ARM instructions. And what is a good compiler? It should generate a correct code. And the target code should run fast. Okay? And the compilation time should not take that long, right? So if you compile and you wait 1 week, then even though it generates efficient code, it's too it takes too long. But some research compiler might take 1 week. So when I was at school, University of Illinois, there is a famous group called the Impact Compiler Group. The compiler was used for Itanium processor compiler. So it was the basis for this commercial compiler, and they do lots of optimization to generate efficient code. Efficient code means the code should be as small as possible and it should run fast. But to do that, they need lots of optimization. They look at different instruction combination and should come up with the best solution. Right? It takes lots of computation, and sometimes it takes more than a week just for compilation for a spec benchmark application. And it should support separate compilation. Separate compilation means each function or each file should be compiled independently to generate relocatable object file. Right? So usually all the compilers support this kind of separate compilation. It should give some good diagnostic messages. Right? If something is wrong, they should provide good hint, what is wrong, and so on. Okay, and compilation phase can be also divided into multiple stages, starting from lexical analysis, syntax analysis, intermediate code generation, which is machine-independent assembly style machine instructions, and then it do lots of code optimization and target code generation, and then it generate an executable file. Lexical analysis is like the function is program is a collection of statement. Statement can be for statement or while statement or assignment statement and so on. It's like English sentence. And the program, as a result of lexical analysis, it actually generates a series of tokens. Tokens can be, if I compare to English sentence, let's say he ate an apple. So he become pronoun, verb, an article, right? Indefinite article, and noun. So it breaks down the statement into different components. So maybe for statement can be, for is a keyword, I is a maybe variable or identifier, equal or colon equal can be an assignment operator, 1 becomes a number, two becomes another keyword, 10 becomes another number. So it breaks down into a series of tokens. Okay? So this phase is called lexical analysis. After this lexical analysis, it generates a sequence of tokens, and then from the token, the syntax analyzer or syntax analysis phase, they try to find out whether this is a valid sentence. To do that, they build a tree. So pronoun becomes a subject, verb becomes a verb, and article and noun becomes a object. Okay? So this is like subject, verb, or object. So it's for English there are 5 standard forms of sentence, and this becomes maybe form 3 or type 3 sentence. Okay? So this becomes a valid sentence. Sometimes if there is no verb, it's not a valid sentence. So by forming a tree, you can figure out whether this is a valid sentence or valid statement. Now, for high-level language programs. Okay? That's called syntax analysis. So you build a tree and intermediate code generation part from this tree, so there can be multiple trees, and they form a valid program syntactically, and then you can do bottom-up or top-down scan of this tree. This is called parsing tree, and syntax analysis is also called parsing. And then during this bottom-up or top-down scan, it generates some intermediate code. So to do this kind of function, you have to do an assignment, or have to do a load, or something like that. Okay? And they also do some semantic analysis during this intermediate code generation, whether this sentence, even though this sentence is syntactically correct, sometimes semantically it may not be correct. For example, he ate an apple can be a valid sentence, but he ate an elephant. This can be a valid sentence or may not be a valid sentence depending on the context. I heard the news from the internet that maybe 1 year or 2 years ago in Africa, a small town, they ate an elephant together, right? They hunt an elephant, they ate an elephant. So in that sentence, this might be a valid sentence, okay? But in general, this might not be a valid sentence because usually we do not eat an elephant, but he ate a desk. This can be also invalid because this might be a valid sentence only in science fiction, okay? Or in a robot or whatever, a strange word. So they do some semantic analysis from the bottom-up scan or top-down scan of this parsing tree, and they generate machine-independent intermediate code, which is more like assembly language instruction, but machine-independent format. Okay, and this part is called front end. compiler front end. It generates from the source program written in a high-level language program into a machine-independent intermediate code. Okay, front end. And the back end is from here. It tries to do optimization, but code optimization depends on the machine microarchitecture. Depending on what kind of machine, the instruction combination, some instruction combination might be more efficient than for the other combination. Okay? So here they do lots of optimization, code optimization. And this is the main research topic for compiler research. Compiler research. Okay, because this front end process is usually most of them are automated. There are many tools you can build front end easily with existing tools. So there are tools called LEX for lexical analysis, YAC for syntax analysis, and so on. So for C compiler, you can develop a C compiler as a course project in a compiler course without that much difficulty, but not much code optimization because this is quite difficult to generate efficient code. Okay? And then it generates target code for the machines. Object code. So you can decompose compiler 5 phase into front end and back end. So front end is machine independent, right? Because you generate machine independent code, right? But this is language dependent, right? So if you are a Microsoft person, you are trying to develop some C compiler, you can use the same front end, C compiler front end, for other machines, such as maybe IBM PC. You should use the different back-end optimization for IBM PC compared to PC. They use x86 instruction set architecture, and they have different microarchitecture also. So front end is language dependent, back end is machine dependent. Okay? Okay, so this is a general introduction of compiler and translation process. And let's go to instruction set architecture and machine language. As we have discussed, instruction set architecture, to design a machine, you have to define machine instructions, the set of machine instructions, and each machine instruction, as a result of execution, they update the machine state. So defining machine instruction involves defining machine state, what kind of registers and how many registers the machine has, and also how many memory locations, memory address you have. So we need to think about machine state, and there are two states. One is registered, the other is memory. It's simple, just registered and memory. And machine instruction either update register or memory location. So what is register? So you have studied flip-flop, latch or flip-flop. So one flip-flop is a static RAM cell, right? Because it has a loop. Loop means as long as power and ground signal is supplied, you can retain your state, right? Because of loop, you are keep writing value. That's static RAM cell. Dynamic means even though the power is supplied, you lose your state because of leakage current. Okay. So flip-flop stores one bit of information, and register for 32-bit processor, each register should be also 32-bit because 32-bit processor means they are doing 32-bit computation, and the default data size is 32-bit. So register size should be 32-bit. So one 32-bit register contains 32 flip-flops. 32 flip-flops. That's the register. So So this register stored data fetched from memory. So by using instruction, you can copy some memory data into a register, or from the register you can copy them to memory. Okay, it stores data. There are some registers that can contain instructions, but it's controlled by the machine, not by you. So programmer has only control for the data registers. Okay, the processor fetch instruction automatically. Okay, and register is internal. It's inside CPU. Usually, register can be read or write very fast within a single CPU cycle. You can read in a cycle. And for all RISC processors, all the computation, including logic operation, should be done only for registers, register operand. Okay, that's the RISC architecture. To do the computation, you bring the data into a register, and then you can do the computation. For CISC architecture, you can do computation on memory data, but it's complex and sometimes the operation takes too long. That complicates the machine design and they slow down the machine. So CISC design is not used since 1980s. So if you want to design a machine, you have to design in a RISC style, which means you have to copy data into a register. And the MIPS instruction set architecture we will study in this textbook. MIPS is a 32-bit, there are two, 32-bit MIPS and 64-bit MIPS architecture also, but you're studying 32-bit MIPS architecture. 32-bit MIPS instruction set architecture has 32-bit registers, and each register is 32 flip-flops. Okay? So register is the fastest memory in the computer system. Okay, it's on the top of the memory hierarchy. There are some fast memory, there are some slow memory. Fast memory is usually expensive because each cell is quite big. It's expensive. Slow memory is cheap, but it's very, very slow compared to registered. Reading or writing into a register takes less than a cycle usually, but writing or reading to a hard disk takes maybe 10 million CPU cycles or something like that. It takes a long time. Okay? And memory here is a DRAM, main memory. And as we have discussed, memory is quite far from the CPU. If you want to access the DRAM, you usually go to op chip, okay? Go to the system bus and chipset, memory bus, and then DIMM card and the DRAM chips. It takes a few hundred CPU cycles. So because it takes too long, you usually use cache, which stores recently referenced data or instruction. And caches are SRAM, memories are DRAM. So it's electronically it's faster, but it's closer to the CPU. And because CPU becomes faster and faster, memory is slower and slower. The speed of CPU, the advancement is faster. So memory becomes distant, more distant as time goes by. So you have multiple levels of caches usually. So as you have seen in the commercial processors, on chip you have first level cache, second level cache, and then third level cache of chip, and then you go to memory. Okay? Registers are visible to programmers, which means to the programmer there is only register and memory. They don't care about cache, memory, hard disk. They only care about memory, which is actually a virtual memory. Programmers view of some address space. Okay? And this main memory, DRAM, is called physical memory. So there is some difference. But this translation, it's done by, this part is done by hardware, and this part is done by operating system. We'll study how memory access are performed. So caches are invisible because to the programmer, there is only registers and memory. So it's same as like this. To the programmer, there is only this kind of instruction: load R1, R2. This means if the register R2 contains 1000, 10,000, then from this content add 100, which becomes this address. From this address, load 4 bytes and store into register R1. So to the programmer, there is only register and memory. Memory for 32-bit processor, if they use 32-bit address, as we have discussed, this is a linear array of bytes starting from 232 minus 1. Okay? So this means address 10,100, 101, 102, 103. There are 4 bytes. Copy this byte and store into register R2. Okay? So only programmer, they care about memory, which is virtual memory, and registers. Okay? Cache is a microarchitecture structure to speed up the memory access. Okay? So memory is a large single-dimensional array starting at address 0. To access data item in memory, the instruction must supply an address. And memory contains a program. So you have compiled the program, it generates executable file, .exe file. .exe file contains both instructions and data. Okay? And this program that contains instruction and data are copied into this address space. Okay? And then you fetch one instruction at a time. There is a starting address for the instruction. The processor copies one instruction at a time from the memory, and then it executes. As a result of execution, sometimes it copies the data from memory as well, and do the computation and store back. Okay, some of these addresses are mapped to input or output device. So you do the input and output device by doing load or store. Okay, that's the machine. So transfer data. Load means you copy memory data into a register. Store means the other way around. Okay. So word is the more accurate definition is the basic default data size for computation. Okay, and also the word is the default data size for a load instruction. If you do a load, it means a word. If you want to load half word or different size data, then you have to specify. So the load instruction sometimes have to specify the data size. So data there can be. So if you do a load, it means load word, same as load word. But you can do maybe load byte. It means you copy just a single byte. 자, 요 줄에 하나, 둘, 셋. 자, 스택 탑. 어디 아픈가? 아니면 뭐야? 아프진 않아? 사탕이야? 아니? 오케이. So you can copy different data by load byte or load half word or load double word. Okay. For 32-bit processors, if you do in a C program, you have integer A. All these integers are 32-bit integers. for 32-bit processors. Okay? But in a C program, you have some short integer, short b, right? This is actually 2 byte, 16-bit integers. Okay? So to copy this variable into a register, you have to use load help word. Help word means help size word, which is a 2 byte word. Okay? Or character. Character is a single byte object. One character is represented using 7-bit ASCII code. It has extra bit. So you store one character in a single byte. So if you want to copy a single character into a register, you have to use load byte. Okay? And float. This is floating point variable. It's actually 32-bit floating point number. Floating point number, real number. And if you use double, this is 64-bit floating point number. If you want to copy this object into a register, you have to use load double word, which is you are copying 64-bit data from memory into a register. Okay? So you can specify the object type, data size by this how do you call appendix or something like that. By adding this kind of specification, you can either load 32-bit or 64-bit or 16-bit depending on the size of the content. 자, 요줄의 두 번째 장애 들고 있는 게 아닌가?
DDW.
This is load double word. Okay? Double word means double the size of the word, which is 64-bit data. Load word 32-bit. Okay? So for 64-bit processors, if you do a load, then it's copying 64-bit data. If you are doing double word, it's copying 128-bit data. Load half word means 32-bit. It depends on the processor word size. Okay? So the same C program compiled for Pentium 4 or i7 will be different because the data size will be totally different. Okay? Byte addressability means every memory location has an address and each location has just 1 byte. Each byte has an address. This is called byte addressable. The first computer, one of the earliest computer was called IAS computer. At the time they used word addressable. Each word has an address. But nowadays all commercial microprocessors, each byte has an address because you want to manage single byte or single character operation. To do that, you need each byte should have an address. So that's called byte addressable. And usually in a memory, all this object means data, either data or instructions. Okay? Instructions or data can be integer, floating point or character, should be aligned. Aligned means their starting address should start at multiple of their size. So if there are integers for 32-bit processors, integers should be aligned at the word size, which is 0, 4, 8, 12, 16, and so on. Okay? Or for 32-bit processor, such as MIPS processor, instructions are 32-bit instruction. All the instructions should be aligned as well, which means instruction address should start at 0, 4, 8, 12, 16, 20, 24, and so on. Characters are naturally aligned because they are bytes, right? And short integer, half word should be aligned at even address, and so on. Okay? And floating, maybe 64-bit floating point data should be aligned at 0, 8, 16, 24, and so on. the multiple of 8. Okay? And so if the processor generate this kind of misaligned address means we are trying to load some integer data, so the address should be the multiple of 4, right? Or 1000 or 1024, something like that. But if you generate misaligned address such as 1023, it can be a fault, which means your programs are wrong and it should be terminated. Or sometimes in another machine, it runs slower. You generate some instruction, then it can accept and try to fetch that object, but it runs slower. Okay, so usually if generated by the compiler, it generates aligned memory addresses are all aligned. Okay. Okay, go ahead.
그러니까 저렇게 이렇게 짝수로 들어간 이유가 그 16바이트짜리는 저기 0, 1에 같이 들어가고
16빗?
네, 16빗짜리는 0에 같이 들어가고 2, 3 같이 들어가니까 이렇게 두 개 단위로 끊어서 공간이 필요해서 이렇게 들어간다 이거죠.
그렇지. 그런데 그렇게 홀수로 you can store other address if you want to. But usually the machine, the machine trying to support misaligned address, it's usually slower because all of them are optimized for this aligned address. So if you generate some alignment, it's multiple of 4, 0, 4, 8, and so on for word size object. But if you're trying to reference this kind of object, it usually involves copying these two words and try to extract. It runs slower, or some machine, they don't allow this kind of misaligned reference. It generates a fault and it actually terminates the program. It depends on the instruction set architecture. So if you look at, when you do debugging for your first project, you will see all these objects are aligned at their natural boundary. Okay? Okay, let's look at the inside machine instruction. So machine instruction, there are two components. One is opcode, the other is operand. Opcode specifies the operation. Operand specifies the data, input or output data. Okay? So the example of this opcode are add, which means addition, subtract, multiply, divide, right? All the computation, or AND, or exclusive OR, they support all this kind of logic operation also. And load, store, jump are one of like go to, okay, branch instruction. It specifies the operation, okay. The other parts of the instructions are operand. It specifies the object or data, okay. And the operand can be registered or memory. It can be classified into register operand or memory operand. Also, it can be classified into source or destination. Source are input, destinations are output. Okay? And so if you have add, we have some example. Okay. For add instruction, it can be like add R1, R2, R3. So this is the opcode, and there are three operands. These two are source. This is destination, and all these operands are register operand, because this is arithmetic computation. As we have discussed, all the computation should be done on register operand. Okay? For load, this is the operation opcode. This is the destination, okay? And this is the source. This is the memory operand. This is the register operand. This is the source. This is the destination. Memory operand, you just specify the location, address. Register operand, you just specify the register number. Okay? That's the operand. And instruction types. What kinds of instructions are supported in a machine instruction? In general, you have 3 types of machine instructions. The first type is arithmetic and logic operations, logic instructions. That's doing computation. So add, multiply, divide, floating point divide, floating point add. Okay? For floating point computation, you need different instruction, different operation, because arithmetic computation we studied. That's the next topic. After we study instruction set architecture, we'll study linking, and then we'll go to this computation, how the computer do arithmetic. So it's an extension of adder, subtractor you have studied in the digital logic. By combining adders or dividers with the registers or other logic, you can implement multiplier, divider. Also, you can implement floating point adder, divider, and so on. Okay? And shift, left shift or right shift, arithmetic shift right or shift left. There are various other operations. These are computation. So it's called arithmetic and logic instructions. The second type is called data transfer instruction or memory instruction. Basically, it's load or store. Okay, you move data from to registered to memory.
What does F mean in front of divide and add?
Divide, F, floating point. Floating, F, floating point. And as I told you, input or output instructions are implemented by memory instruction. There is no separate input or output instruction. You do a load or store and you can perform input or output, because some of the memory locations, so there are some instructions and there are some data. Some of these data addresses are mapped to I/O device, such as printer or scanner or mouse. If you load from a mouse address, then you are trying to input from a mouse or keyboard. This is called I/O port. I/O port. If you are trying to write to a network port, then you can transmit the data through the LAN and it goes to the internet. Okay? So by doing load or store, you can do input or output to output device. And this is called memory mapped I/O. Memory mapped I/O. Okay? I/O devices are mapped to memory address space, and this address are called I/O port. I/O port. Okay? So this is called data transfer instruction. You can, using the data transfer, you can load or store the data from memory to a register or vice versa. And you can also do input and output. The third type of instruction is called control transfer instruction or branch instruction. It changes the program flows. So the function is trying to modify trying to specify the next instruction address. Okay? Without this branch instruction, you just keep fetching an instruction one at a time sequentially. because the instruction is 4 byte in a MIPS processor, you just need to increment your program counter by 4 because it points to the next instruction because instruction just stored sequentially. Okay? So by adding 4 to your address, you can fetch next instruction one at a time. But if there is a branch, you try to change its control flow. If this is a jump, it can go to any location. Okay? And these control transfer instructions there are unconditional branch and conditional branch. Jump means it's like jump to this location directly. This is unconditional. Function call or procedural call is also unconditional. You do a function call. Okay? Return is also unconditional. You go back to the call side. It's called call side. You can call this function A from different location. You can call function A, you can call it from here, you can call from here. These are called call side. Side is a location, right? Call side. So you are going back to the call side, right? For the return. Branch equal is a conditional branch instruction. You branch if the example of branch equal is like BEQ R1, R2 loop. If R1 and R2 are the same, you go back to loop. And you are doing iteration until this condition is met. Otherwise, you go to the next instruction. This is called conditional branch. Conditional branch. You can have branch equal or branch less than or branch greater than or equal to or something like that. There are lots of other relational operators you can use for the branch instruction. So you have 3 types. Computation, which is called arithmetic and logic instruction. Data transfer or memory. And control transfer or branch instruction. Okay? Let's look at one level deeper. Okay? So you are trying to encode this opcode and operand information in a 32-bit instruction. Okay? You are trying to encode this information. And for MIPS, 32-bit MIPS machine language, there are 3 different formats of encoding. And this slide shows two of them. One is called R-type, I-type, and the third type is called J-type. There are only 3 formats. Because MIPS is a RISC architecture, you are given only 3 types of instruction format. For x86, there can be many more variations. Okay? Because that's CISC. This is a RISC. So it's quite simple. R-type, R means register type. Register type. So there are only register operands. So this should be used for arithmetic and logic instruction because all the computation are done for register operands. Okay? So here, R-type format instruction, the first 6 bit specifies the operation. So there are 6 bits. So you can specify approximately 64 operations using this format or 64 instructions. So opcode specify the operation. RS, RT are source. The first source register source operand, the second register source operand. Each register operand contains 5 bits. So using the 5 bit, you can specify 32 registers, right? Because there are 5 bits. And MIPS contains 32 registers. Okay? So you can specify one of these 32 register as a first source, second source, the third register operand becomes the destination. So if you are trying to encode this information, R2 becomes RS, R3 becomes RT, R1 becomes destination. Okay? So here they encode the number. RS becomes 2. So it should contain 0, 0, 0, 1, 0. Okay? 0, 0, 0, 1, 1, and 0, 0, 0, 0, 1. Okay? And for add, you can look at opcode table that are specified by the processor instruction manual. Okay? And shift amount, this field is used for shift instruction. It specifies how many bits you are trying to shift. So you can shift to or left or shift right. So for 32 bit, you can shift maximum 32 bit. So it requires 5 bits of information. You do a shift to left, one bit, or shift right, 2 bit, and so on. Okay. Actually, for R type, what they do is, this is the basic opcode, and function fields specify the specific operations. I don't remember exactly right now, but for arithmetic and logic operation, the opcode should be all zeros. And actually add, subtract, multiply are specified from the function field. Okay? Because this same opcode can be used for branch or other instructions. So operations are specified using opcode field and also function field. Okay? For other instruction format, using this opcode, they specify all the operation. So if only for arithmetic and logic instructions, opcode should be 0, and the function, using the function field, they specify the operation. We'll look at some example. How do they encode the information? Let's look at I type. I type is called so you have same 6-bit opcode, but you have 2 register field and 1 address. So this is used for load or store instruction. Load or store instruction. RS is a base register. Base register, what is base register? So here, as I said, this is specified memory address. And the R2, to compute the memory address, based on the content of R2, you add this amount. This is called offset or displacement. Offset or displacement. And this register is called base register. Base register. What they're doing is, you can store in memory, maybe there is an array called A. From A0 to maybe A100. Right? Base address, the base starting address of this variable A, you can store into register R2. And A0 can be referenced by 0, R2. A1 can be referenced by 4, R2, and so on. Right? Because this is integer array, and for 32-bit processor, each integer is 4 bytes. Okay? So base address is like, it contains the start address of some object. Using the displacement or offset, you can specify specific element or specific location. And this register is called base address. Okay? So the first register field becomes the base register, and this becomes the displacement or offset. Okay? This address is usually specified by 2's complement number. So you can specify plus minus 2 to the power of 15, right? So you can, from the start base, you can go back or go forward. Okay? So this becomes the memory operand. Okay? If this is a load instruction, then this becomes the source, and this becomes the destination. Okay? If this is a store instruction, this becomes the destination, this becomes the source. Okay? So RT can be a source or destination depending on load or store instruction. Okay? Or it can be used for conditional branch instruction, such as this branch equal. Branch equal. Branch equal. If R1 is same as R2, you go back to this label. Okay, so R1, R2 becomes RS and RT. And this address, if there is 1, 2, 3, 4, 5 instruction, this becomes you go back to -5. Or if there are 1000 instructions, you go back to -1000. Or you can, based on this address, you can go to maybe this address, another target. That's plus. You can do a forward jump or backward jump. Using this displacement, you can specify you are going backward, which is your loop, or you can go forward. Okay? That's the for conditional branch instruction. But you use the same instruction format. Okay? So, sometimes you need to specify memory address, right? So, this base register plus address, you can specify some memory address. Here, you also specify instruction address, right? You go back to 5 instruction, or you go for 10 instruction, and so on. And there are different ways of generating the address. This is called memory addressing. The example here is the example used for load or store instruction is called base addressing. The memory address is the sum of register content and a constant called displacement. Okay? So here it's trying to load one word from this location into a register called S0. S0. And this means this is a base register and this is an offset. You add this offset to the content of this register. And this becomes the address of the object. Okay? This is called base addressing. If you use base register, it's called base addressing. So MIPS supports 1, 2, 3, 4, 5 different ways of addressing. And you have seen this one also, PC relative addressing. Address is the sum of PC and a constant. So here branch is equal $S0, $S1, R1. If these two registers are the same, you go to this label. Okay? So here, from here, we are going to this location. Program counter points to the current instruction. Okay? By adding this -5, because there are instructions are 5, you should do -5 times 4. Right? But you are adding minus or plus relative to the program counter, right? To generate next instruction address. This is called PC relative addressing. PC relative addressing. This is used for conditional branch instruction. Okay? Based on the current location of the instruction, you can jump back or jump forward. Okay? And there are other modes as well. So we have studied base addressing and PC relative addressing. So register addressing, you can specify address by a register directly. And this is used for return instruction. Return instruction. This is actually a return instruction, jump register. And this is called return address register. You jump back to the address that are in this register. Okay? To understand this, you need to understand function call. Function call. So you can call function, let's say procedure call function A. You can call another function A. Inside function A, you have a return, right? Return. And inside function, you can call function B and so on, right? Inside function B, you have maybe another function called C. So the procedure call sequence can be, maybe there are main call, okay, main call A can call B can call C might be a recursive function, you can call C, and then return like this, right? So this structure is function call, the machine instruction that are correspond to function call is called jump and link in a mixed machine language, jump and link. And return is jump register $array. There is a register, special register called return address register. So the function of this jump and link A is you jump to memory location A directly, but you do a linkage because you have to store your return address somewhere. Because when you go back, if you call from here, then you should go back here, not here, right? So you need some kind of linkage between function call and return. So what they do is whenever they do a jump and link, they jump to location A, and at the same time they put return address. Return address should be the next instruction after this instruction. So that can be PC plus 4, right? For the return address, they store their return address into this special register. Okay? So after they do this function call, finally when they do return, they just jump to the location that are specified in this register. Then they can always go back to the call site, right? Wherever they are called. Okay? This is called jump and link instruction. It's used for function call or procedure call. Function call means there are some return values. Procedure call means there is no return values. Okay? And we also study how we can transfer argument because we are implementing functions or procedure call. We need to specify what kind of argument we are sending to the procedure or function. Okay? So sometimes the return address is specified by a register directly, and this is called register addressing because the address is specified in a register. Okay? And there are some instructions such as add immediate. So maybe add I, R1, R2, 10. This is a source. You add 10 and store it into R1. So for small constant, you can specify directly in the instruction. And this is called immediate. Okay? Without immediate, what you should do is you store this another operand in the memory. You have to do a load, and then you have to do a addition, and then store. And then you can store back to this, you can do the computation. But that's slow, right? For small constant, you can specify directly in an instruction, and this is called the immediate. Okay? So, for small constant operand, you can specify the data itself in an instruction, and this is called immediate, and this is called immediate addressing. It's not actually address, it's the data itself. Okay? And finally, pseudo direct addressing is the address is the 26-bit offset. As in this example, this is jump and to location L1, and this J type all three different instruction format opcodes are specified by the first 6 bit. For J-type, you have remaining 26 bit. 26 bit. You can specify using this 26 bit address, the memory address directly. So this 26 bit concatenated with the upper bit of program counter, you can specify instruction address. That means so to the programmer, memory is a linear array of bytes. So for 32-bit address, you have from 0 to 2 to the power of 32 minus 1. Okay? And each one has a byte. And what are stored in this memory? Program. So memory only contains program. So usually there are two components. One is code, instructions. The other is data. Data means all the variables you are defined. Integer array, characters, floats, and so on. Okay? And instructions. And so these are instructions, and it's so-called text area, txt. And there are some static data. There are some dynamic data. Static data are all global variables, or all the variables declared as static integer, and so on. Dynamic are classified into stack and heap. Heaps are data allocated by malloc or free, right? Dynamically allocated. Stacks are all the variables defined inside function that are declared whenever you do a function call. You have to relate when you return because it's dynamically allocated. Whenever you use the function, you allocate. When you return, you deallocate because you no longer use those variables. And it's dynamically allocated. Okay, and the instructions are only here. The jump is used only within this range, and 26-bit is enough because you don't use entire space for the instructions. And the program counter has all 32-bit, so you only need to change this LS bit using the 26-bit, and you can specify whichever location in this text or instruction area. Okay, it's called pseudo direct. It means to specify instruction address, you actually need 32-bit, but you can share upper bits of program counter because that are in the instruction space. So by using 26-bit, you can directly specify whatever instruction address you need to specify, and it's called pseudo direct. It's almost direct. Directly encode the target address in your instruction. Okay? Let's look at example. So we are trying to specify this instruction, add A, 9, 10 and 9, 10 is your input and this is the destination. We are trying to add register 9, register 10, do addition and store into register 8. Okay? And as I said, this should use R-type instruction format. Okay, RS, RT, RD. And RS, RT is source, RD is destination. Okay? So 9, 10 should be the source, A should be the destination. So RSRT contains 9, 10 in decimal, right? And 8. And there is no shift instruction, so we don't use shift amount field. And how do we specify add? We have to look at their tables. Add should be specified by opcode 0 and function field 32. Let's look at example. So this is somewhat hard to read, but this is opcode field. All the R format instruction, the opcode should be all zeros, right? Because they specify the operation opcode by the function field for the R type. Let's look at function field. These are the function table. Try to find out add. Add is where? This is an add. Add is, this is MSB, this is LSB. MSB stands for most significant bits, least significant bit. So add are 1000000. So this corresponds to 100000. In decimal, that's how much? 1 and 5 zeros. That's 32, right? So 32, and this is 0. So this is the instruction in decimal number for each field, and you translate into binary. So 000. These are 6-bit, 6 zeros, 5-bit register operand, and then 0 and 32. And when you represent long binary number, you use hexadecimal for compact representation, right? So if you divide by 4 bits each, this should generate hexadecimal numbers for this instruction. So in hexadecimal, this becomes 0, 1, 1, 2, A, 4, 0, 2, 0 in hexadecimal. Okay? And so this is the machine instruction for this assembly instruction. Okay, 여기까지 합시다.